Hello and welcome. Today we're going to be talking about time-dependent PDE solutions and the technique to solve them, which is called separation of variables. So let's get down to things here. So in previous videos we've talked about finding equilibrium solutions. Okay, so these are time independent solutions. So here we have a general u x of t, some density of stuff, some sort of quantity of stuff in space and time, and of course we're moving it to just this. So that's an equilibrium. In today's video, though, what we're going to find is we're going to now find u of x comma t. All right, so a function that's going to be, by definition, multivariate. Okay, so the type of problems we're going to do are going to be, of course, linear PDEs. And the technique is called separation of variables. So separation of variables is a technique that requires a certain thing. So the PDE must be linear. Okay, so it has linear operators in space and time. Okay, so that's the first condition. Two, and another one they have to be separable. And what this means is essentially your PDE has to be of the form LT of u equals LX of u. And in this here, what we have here is this is going to be a temporal linear operator, and this one is going to be a spatial linear operator. So it's best to give an example of what we're talking about here. Let's talk about the heat equation. So the heat equation states that so in this case LT is just going to be the first temporal partial derivative, and here Lx is going to be the second spatial derivative multiplied by that diffusivity parameter. So again, it's pretty straightforward. Separability means, though, of course, that what's really important here is that it's also homogeneous. So what we see here, there are no sources or sinks. Okay, we don't have any additional term, so basically there can be no terms that don't depend on u in a linear way. Okay, so that's ultimately, though, what we're talking about in the context of heat transfer would be there's no sources or sinks. It has to be a homogeneous problem where the only heat transfer is through flux. So in this video, let's focus on this heat equation, and we'll come up with the technique for a separation of variables. So let's do it. So separation of variables. So we're going to talk about the steps. Okay, so the way we're going to do it is, so there's going to be 6 total steps, although I'm sure you could break them down into more or fewer steps depending on how, where you want to subdivide things. But there's 6 basic steps going on here. And what we're going to do is we're just going to list off the steps, and we're going to look at specifically, we're going to solve a particular PDE, which is that heat equation. With the boundary conditions, which is just going to be 0 temperature boundary conditions. So U of 0 comma T is going to equal 0, and U of L comma T is going to equal 0. So here we have a bar, like a rod that starts at 0 and goes up to capital L there, we want to figure out what to do there. Okay. All right, so let's talk about the first step. The first step, of course, is to separate the PDE into the spatial and temporal operators. So in this case, we want to find an LTU is equal to LXU. Okay, and so specifically, we already have it here. We have a UT is equal to DUXX. So the heat equation, as written like that, is already in separated form. We have all the spatial derivatives on one side and all the temporal derivatives on the other side. Okay, so that step is pretty straightforward. It was really already done for us. The next step we want to talk about is we have to do the actual separation. Separation of U of X into time and space factors. And what we mean by this is we're going to take U of X comma T and we're going to factor it into two univariate functions like this. So U of X comma T is now going to be actually composed of two univariate functions. All right, and so this is actually not, we're not even sure can we do this. Can we do this? And the answer is we don't know. This is actually an assumption. This is an assumption. Sorry, let me write that a little clearer here. That's an assumption. That's an assumption we hope is true in order to solve. So it turns out, of course, as we'll see, as long as your PDE is separable, which means that we can factorize, we can separate the spatial and time derivatives, and that we also have homogeneity. So it should also be noted that we require the boundary conditions to be homogeneous. Okay, that is another requirement of separability. Okay, so we don't know if this is true, but we're gonna hope it's true in order to solve this thing. All right, the next step is to with number 2 is now we have to plug in. We're going to plug in our U is equal to P times Q into the PDE. All right. So in this particular case, what we're going to do is we're going to take LT U is equal to LX U. If we write it this way, LT is equal to PQ. and that's equal to Lx is equal to PQ. Actually, let's be a little bit clearer about what we're doing here. Remember, this is P of x, Q of t, and that is equal to Lx of P of x, Q of t. So, of course, this is time only. So we should be able to move so we can just operate LT is just going to only operate on Q, and P is actually going to come right outside of it because it's a linear operator, and this is effectively a constant. And on the other side, this is, of course, space. So we should be able to bring the Q of t outside and have Lx of P of x. All right. Now, if I was going to do this to my heat equation, let's just follow along and do this particular problem here, is we have a time derivative of P of x, Q of t, and that's equal to that double space derivative of P of x, Q of t. So we put these through, what we're going to see here is that we're going to have a P times Q prime on this side, and a Q times D times P double prime on that side. So this is, of course, for the heat equation, we see how that separation works in that particular example. Okay, so from here, now what we want to do is separate time and space functions. And so what we're going to do is we're going to take this and move everything over that doesn't involve. So we're going to get it as an LT of Q over Q is equal to Lx of P over P. So what we did is we just divided this equation by P and Q to get it separated in this form. So in this case here, everything on the left-hand side depends only on time, and everything on the right-hand side depends only on space. And we can do the same thing with our specific example. Oh, it looks like I made a little mistake, a typo here. That should be Q here, Q prime. And so what we're going to get here is Q prime over Q. I'm going to put the D with the Q, and we'll see why that is the case. And then we have a P double prime over P. All right, so remember that everything on the right-hand side is space, and everything on the left-hand side is time. And the constant D, I will place it on the time side, but in reality, you can place it anywhere you like. It turns out it's a little easier to always put the constant with the time side than the space side. And we'll see why in a little bit. All right, so there is our separated equation. Okay, next page. Right, and now number 3, the next step is to do the eigenvalue formulation and solution. So this is where things maybe take a turn in a little bit, in maybe a place that wasn't so anticipated. Remember what we have here is we have an LT of Q over Q is equal, and this is of course a function of only time, and here we have an Lx of P over P, and this is a function only of space. So what we see here is if two functions of distinct independent variables are equal, then they must be equal to a constant. And think about that for a moment. If I move t, and if I change x, and I can change them independently, so if t and x change independently, but somehow whatever is on this side, which is only a function of time, must be equal to Lx of p of x over p of x. They have to be equal to some constant. And it should be noted that this constant at this point in time is unknown. Okay, so there's our lambda, and this is the equation we have. And what I really want to focus on is this right here, our spatial equation. So we see now that that gives us now an eigenfunction problem formulation, where we have Lx of p is equal to lambda p. This is all of x, subject to the boundary conditions, which are homogeneous, that forms an eigenfunction problem. Okay, so of course, previously in this course, we've worked out many examples of different eigenfunction solutions, and now we see how that tool is used here. So assume we have solutions. We're going to have a Pn of x and a lambda n are our pairs, and n starts at 0, 1, 2, 3, and so on and so forth. Suppose you find these. Okay, so we haven't found them, but let's go do this. We'll do an example of how this works. Remember, we had the following equation. So this is with our heat equation. We had Q prime over Q times D was equal to P double prime over P, and that is of course equal to lambda. We're going to take just that right there, and what we have is P double prime is equal to lambda P. Okay, and then we have the boundary conditions. P of 0 is equal to 0, and then P of L, that's x is equal to L, the other end of the bar, is equal to 0 as well. Right, so you may recall from previous videos and also the textbook that this has a specific solution. The eigenfunctions are going to be P of n of x is equal to sine n pi over L x. And then we have lambda n's equal to negative n pi over L quantity squared. Okay, so here's our eigenfunctions, and n goes from 1 to 2 to 3 to 4 to 5, and so on and so forth like that. So these are our eigenfunctions. And of course, you can probably spend some time and actually discover that that is in fact what the eigenfunctions are. We want to keep this video not too long, so I'll just leave them there, that we can, in any of these cases, we should be able to find the eigenfunctions. All right, so the next step is then, so let's go on to the next step. So now we're going to have step 4, which is solving the time side of the separated equation. So recall, what we had was Q, LTQ over Q was equal to LXP over P, and that was equal to lambda. We found lambda n, where n goes from wherever it starts. I'll start here at 0, 1, 2, 3, and goes up forever. And then we also found Pn of x that goes with it. So there must also be Qn of t that goes with lambda n as well. And that's the whole point here. The point here is that space and time are yoked together by these special numbers, these eigenvalues. Okay, so what we can solve is, so what we need to do is solve LT Q of n of t is equal to lambda n times Q of t. All right, here we have no boundary conditions. We have no boundary conditions, so assume we can solve these. Qn of t, it's equal to something, right? We'll say that we know what it is, but let's just do a specific example. Let's go back to our heat equation. So the heat equation, we had Q double prime over D, or Q single prime over D times Q was equal to P double prime over P, but now we have those Pn's, and then we know that's equal to the lambda n's, and the lambda n's can actually be written this way. It's going to be n pi over L quantity squared, and n is going to start at 1, go to 2, 3, 4, and up for forever. So that means we need to now find those Q of n's. So let's find it. It's going to be Qn of t prime is equal to negative n pi over L quantity squared times Qn of t. All right, this is a first order linear problem. It has solutions that are exponential. So we're going to have Qn of t. These general solutions are going to be an e to the negative n pi over L. Oh, you know what? We forgot the d. There was a d sitting there. I forgot to write that in. Let's go and write that in. We know there has to be a negative times d there. Okay. N pi squared times d times t. So right there, we would call this the general solution. Okay. So that is the answer for the heat equation right here. So now we go on to step 5, which is recombine the Q of n and the P of n to find U of n of x comma t. Solutions. Okay, let's do it. So what we have here is, so we know that U of n x comma t is equal to, let's write it down. It was going to be Qn of t times Pn of t, and that's going to be from n is equal to whatever those index is. So in the case of the heat equation, what we had is U of n of x comma t is equal to an, that's our free parameter, times e to the negative d times n pi over L quantity squared times time, times, and then the un functions were sine n pi over L x. Okay, so these are the functions that we found. And we found, of course, that there are n equals, not 0. It starts at 1, goes to 2, goes to 3, goes up forever. So there are infinitely many solutions. Those infinitely many solutions, but then recall that the PDE is linear. So, because the PDE is linear, any linear combination of solutions is also a solution. Okay, and that means that our solution u of x comma t, what we're going to call the general solution, is written the sum of an times u of x comma t n. N starts at wherever it starts, let's say 0, and goes to infinity. All right, for our specific example of the heat equation, what we had is u of x comma t is equal to the sum n starting at 1. Again, the starting point depends on the problem and how you've indexed things. It could start at 0 or 1 depending on the specific context. That's really great there. So we have this. There we go. This is our general solution to the heat equation, like that. And that is step 5. We found this general solution. So here, the ANs are those free parameters. Okay, so this is the general solution. It has both, a time variable and space. Space variables. So it's a multivariate function, but in this particular case, it's also infinite. There's an infinite sum of all these different functions, right? Okay, so now the final step is we have to incorporate initial conditions. Okay, if we have an initial condition, we can now find a particular solution. Let's find a particular solution here. Okay, so u of x comma t but now we're going to say that t is equal to 0, and we're going to say at t equals 0, we have a specific initial condition. So this is our initial heat profile in the bar. Okay, for instance, that's what it could be, right? Whatever it is, this is going to be given in the problem. Okay, well that means I can write this now as u of x comma 0 is equal to the sum, n starts at 0 and goes up to forever, of an times q n of 0 times p n of x. And we know that has to equal f of x. So here, so we want to know, can we represent fx as some infinite series of eigenfunctions Pn of x. If so, I should say we're going to write this as f here. I need to back up there and say that, i.e., can we represent f as some infinite series of eigenfunctions? If so, then u of x comma t is our solution to the initial value problem. Okay. So to see how this works, let's do the specific example of the heat equation. Let's do this heat equation right here. So let's say we are given u of x comma 0 is equal to f of x, right? Again, we have this rod. It goes from 0 all the way to L. And maybe f of x is some initial temperature distribution. It's hot at some places in the bar and it's colder in others. But it's 0 at each endpoint. We know that. That's part of our problem. Okay? And so we found this. We know our general solution can be written as this. N starts at 1 and goes to infinity times an times e to the d times n pi over L quantity squared times 0 times sine of n pi over L x. I can rewrite this in a slightly simpler form because I know this term right there is just, it's just 1. So what we have here is a Fourier sine series. So we know, so Fourier convergence theorem states that whatever f of x is, there are an constants that will allow the series to converge to f hat, the representation of f of x. So that's really, really cool. So the idea here is that now our final solution is going to be u of x comma t is equal to the sum, n starts at 1, for the heat equation, that is, an e to the negative d times n pi over L quantity squared t times sine n pi over L times x, where the an's are given by the standard formula 2 over L, 0 to L of f of x sine of n pi over L times x dx. So that is our final solution to the heat equation. And it's it can be time dependent and space dependent, and this solution will work for any problem where you have a bar with 0 temperature boundary conditions, a diffusivity of D, of length L. This will always be your solution. So that's one example of how to use separation of variables to find a specific answer to a PDE where it's both time dependent and space dependent. Thank you very much. In future videos, we'll solve more PDEs with more interesting boundary conditions. This is just the beginning, but I think this video is long enough. We'll do more examples in subsequent videos.